So this slide showing the classes of the IP addresses for IP version 4. So we have basically 5 classes, although the first 3 are the main ones. So class A, the first bit is always a 0. Class B, the first 2 bits are always 1 and then 0. And class C, the first 3 bits are always 1, 1, 0. So these give you a range of numbers between 1 and 126 for the first octet. And then these give the range of 128 to 191 in that first octet. And then the class C gives you a 192 all the way up to a 223. And now notice over here, though, we make a special note where the 10 for the first octet, they're looking at the 10 is what they call the private range, which means that companies can use this as internal addressing. 172.16 and all the options between 16 all the way to 31 can be used as private in class B, and 192.168 any of these networks can be used. So remember, we have our street address and then house or building number. So the idea here is we have a network and a host. So what would represent the building or the house number 6200 would be the host, and then you have the network, which are all the devices on that same network. So this slide just shows you the address range for those private IPs. So for the private ones, we have the class A, class B, and class C, and it just shows you the range of possible addresses, including the ones that are actually reserved with the zeros in the broadcast. So this one here now just gives us a count. If you have the network, class A, the network is the first 8 bits. That leaves you 24 bits for the host, which means you can have 16 million unique devices on that network. Class B, you have 16 bits for the network, so you're left with 16 bits for hosts, which still gives you over 65,000. And then the class C, which gives you 24 bits for the network, and that just leaves you 254 unique devices. Again, you can't use the case of all zeros, and you can't use the case of 255s. So that just leaves you 254 unique devices on that network. So if you do a standard class C network, you can have no more than 254 devices, and if you want internet access, one of those is going to have to be your gateway. So what specifies how many bits are the network and how many bits are the host is specified by this concept of this subnet mask, or sometimes they just call it net mask. So if you have 32 bits and you use a /24 notation, or the first, what you're saying here is the first 24 bits are ones, those are the network. That puts you into the class C. And so you're in a class C, which means, again, you're down to just 254 unique devices on your network. So here's an example where I have, say we have A and B, and so say this top address is A and the second one is B, and we want to talk to the other device. And so if we use a /16 here, then we're saying the first 2 numbers, 10.15, is the network, and then the other 2 octets, the 24.5, is a host name. And so if that's the case, then 10.15 and 10.15 is the same network, and so these devices could use a crossover cable to talk to each other directly, or they could be connected into a hub with straight through cables and they can talk to each other. Okay? However, if we change this to a /24, then what that says is this 10.15.24 is the network for the top one, and 10.15.223 is a different network. So B would be on a different network. And so therefore, to communicate, you would have to have a gateway. So you would have to like connect to a gateway device that's most likely connected to your hub. And that same gateway then has to be on the other network, or it can be the default gateway that can eventually route you over to your different network. But you have to have this. But a gateway is always going to be on two different networks simultaneously. So it allows you to basically leave this network and go up to this network. But again, because I have a /24 now, I'm saying that these two addresses are different networks. So this subnet mask is the key to defining whether something is on the same network or on a different network. Okay, I mean the numbers also matter, but where the subnet mask ends specifies that. So a switch or a hub is just a communication device that allows us to build this star topology. A router routes packets out of the local network to a different network. So sometimes they use the term gateway, sometimes they use the term router. Now a default gateway is the gateway that gets you out to the internet or to just any random network. A non-default gateway or the router itself is like the device that gets you out there. The gateway is kind of more of like the logical definition of it. But so again, the default gateway will get you out to any general network. But if you had like a special internal network that did not have, say, internet access, then you might have a different route to route just to that particular network. Okay, so you would have a router that could get, and it wouldn't have to necessarily be the same router that gets you out to the internet. It could be a different router, but you would have a box on both networks that is set up, and then you would have to set it to be your route over to this separate private network. And then a firewall is a security device, or really it's a software program running on a device that looks at these packets and it looks at the addressing and decides whether to leave the packet through the system or not. All right, so now one thing to keep in mind is that the PLCs and the robots and pretty much any of these industrial devices, they cannot do a lot of processing, which means they almost never can do like encryption. And so therefore, you really don't want these on just a general network. These need to be on their own private network and with proper firewalls behind them to protect them from, possible hacks or worms or whatever type of malicious software and packets are on the network. So you want to keep these industrial devices on their own industrial network and keep it isolated and properly secure. All right, so let's take a look at some wireless protocols here and some modulation things. So we'll just talk about a few of these and look at some of the speeds here. So just as a reminder, the bit rate is a measurement of how many ones and zeros can be transmitted to the next device within 1 second. And then the bandwidth, which is kind of a rating of that, but bandwidth is kind of a more general term, just saying the more bandwidth you have, the more bits we can transmit back and forth. All right, so when we talk about wireless, how does that work? Now, I'm sure you've heard of radios or listened to the radio, and you have FM channels and AM channels. So in this slide here, I'm just trying to give you a graphical feel for what AM and FM modulation is. So if you look here at the top, we have our base transmission frequency. So when you like tune into your favorite radio station, like 89.7, whatever station you might want to listen to, that is transmitting on this transmit or this base frequency. And so if we are going to use frequency modulation, basically what we're going to do is we're going to speed up the frequency to send a 1 and slow down the frequency to send a 0. So here we have instead of one full sine wave just in our base, now we're sending 2 sine waves in that same amount of time. So we've doubled the speed of the frequency. Now again, this is just a very simplified version to just allow you to somewhat visualize this. And then so if we're going to send a 0, we're going to send that, we only get half a sine wave in that same amount of time. On the other hand, if we look at the amplitude modulation, up here, notice that this base sine wave, it went from 0 to 1. Okay, that's what we call like a unity rating. So what we're saying here is this is the normal peak value of the sine wave at 1, and then at trough at -1. So it's a peak value is a 1. But with amplitude modulation, what we're going to do then is when we want to send a 1, we don't change the frequency, but what we do is we change the amplitude up here. So again, in this example, we doubled the frequency and that's a 1, or we have the frequency and that's a 0. So so you can kind of visualize now what the difference is between frequency modulation and amplitude modulation. Now, you can actually send way more data faster using frequency modulation. However, you can actually send data further, although not as much, but you can send data further using amplitude modulation. All right, now the problem with frequency modulation is, though, that we're only sending 1 bit here. So they also came up with what they call something called phase shift keying, and basically what this does is it just kind of takes frequency shifting to the next level. So now instead, in this amount of time here, instead of sending 1 bit, I can send more than 1 bit. So in this case, I'm sending, I have effectively about 4 sine waves compared to my base, and that gives me a 1, 1. And then over here, when I send a 1, 0, I'm sending twice as many. And then if I want to send like the 0, 0, then I'm sending a half, and if I want to send a 0, 1, then that's just my baseline value there. So this allows me to, instead of, in the same amount of time, instead of sending 1 bit, I'm doubling the number of bits that I can send. All right, now there's several protocols for wireless technology out there that gives you a long range. One of those is called LoRa, which is just an abbreviation for long range. Another one's called LPWAN, which is low power wide area network. Okay. And again, here you get into these, and I don't know off the top of my head if these actually are using amplitude modulation or frequency modulation, but they give you a lot more range than standard Wi-Fi. So I have this little plot here I found. Here's the link to where I got this graphic at. But this just demonstrates three different things all in one graph. So the color indicates the cost, and the darker colors indicate a higher cost, but the vertical indicates a faster speed, and the horizontal indicates range. So if you see here, you have Wi-Fi, which is up here at the top as far as speed, how much data you can send, but it's kind of low on the distance, right? It's only good for a few meters, where cellular can send, several miles. Usually you can go several miles with cellular, but it is the problem with cellular is it's licensed, which means that you have to pay a cell phone carrier to use that. But then some of these that I mentioned before, like this LoRa, uses what's called unlicensed frequencies, and so they're low cost, and they can actually still go up to, say, 10 kilometers, which is over 6 miles. So it just gives you a demonstration. The other side of this, the next slide here, shows you the battery life to go along with that. So it gives you a lot of the same information in a table form here, but it also kind of gives you an indication of battery life. So when you're using Wi-Fi or Bluetooth, those are really hard on batteries. They use a lot of power, but they can send a lot of data, right? Those are high on the data list, but they cost you in energy on your device to send that data, where the LoRa and some of these other ones listed here are very low power. They can't send a lot of data, right? So the amount of bits per second they send is really low, but they can, because they're only sending just a few bits and they're very low power, you can run them off of a battery at a remote site, and that battery can last for quite a long time. So that's all we're trying to demonstrate with this slide. All right, so let's take a look at industrial protocols now. So there's several different industrial protocols here. This is not a complete list, but these are ones that are commonly found on Allen Bradley Control Logics type PLCs, and also Siemens PLCs on here. And the big three that we're going to kind of look at here, we have Ethernet/IP, we have DeviceNet, Modbus, and Profinet. Those are Modbus, Profinet, and EtherIP are pretty much the most common available nowadays. All right, but I think the one thing to mention about these is these have, at least to some degree, a real-time speed definition on them, so that when you send data, you know that that data is going to be received in a timely manner. So they have a timing mechanism built into them to give us some sort of guarantee that the data will be there received on time. All right, so Ethernet/IP, or industrial protocol, when it's written like this, it doesn't mean internet protocol. It means industrial protocol, which again indicates that it's got this built-in real time. And the way they do this for Ethernet/IP, with the way they do the real time, is up there at that application layer I talked about earlier on the OSI layers, is the application sends out a timing pulse or a clock signal. And the reason they do it all the way up there at the application layer is because Ethernet, actually, when it was originally designed, was designed specifically to be not real time. And so it's kind of a bit of a hindrance to Ethernet/IP because they're sending this clock signal at this high level, because down at the hardware level, because technically Ethernet is the hardware level, and at the hardware level there's no guarantee of real-time communications. So they guarantee the real-time communication through the application layer, and that's kind of why it says here on the slide semi-real time. All right, so let's talk about testing Ethernet on your devices. So if you have a Windows device, we have what's called IP config, which will show you the IP settings of your local device. That's whatever Windows machine you're on. This is a Windows command. If you're on a Linux machine, such as a Raspberry Pi or a BeagleBone, the command is ifconfig. So again, IF for interface. That's your network interface, where IP is your internet protocol. So slightly different commands, but they give you most of the same sort of information. There's also a ping command, which is available on any Ethernet working device in general, which allows you to send a packet or multiple packets across the network to another device, and then if that device responds, you know your network is set up. So that tells you that, number one, both devices are turned on, powered up, and that they have an IP address, and they have the correct wires, and everything between the two is all correct. So it doesn't tell you whether you're going through gateway or not, if you're on the same network or not. It doesn't tell you that, but it does tell you that you can communicate with that device across the network. Then there's the netstack command. The netstack command will show you all your local services, including the ports. So remember, the ports are at the transport layer. So we have the transport layer, we have the internet layer, and then we have the hardware layer, and then of course up at the very top is the actual main application. But at these different layers here, the netstack command is basically showing you information about the transport layer on your local machine. Then we have telnet. Now telnet, a lot of times Windows does no longer give you telnet, and I don't even think it's on the BeagleBone by default. But telnet is kind of handy because it actually sort of gives you both. It gives you the connection between ping and a port on the remote device. So you can only test one port at a time with this. But and technically it's not a test tool, it's a communication tool, and it's all plain text. It doesn't really do encryption, which is why Windows, I assume, has no longer has it installed by default, because it's not real secure for doing remote communications. However, just as a testing tool, it's very handy because it allows you to do what ping cannot. Ping can tell you that that other machine is there, but it can't connect to the port of the other machine, so you can verify that the process that you're running has an open port at that transport layer, where telnet can do that for you. So again, I don't recommend using telnet as a communication thing to send data between two machines, but I do find it a helpful tool sometimes when you're trying to test whether the other machine is actually responding at the transport layer. And the last one here is ARP. ARP stands for Address Resolution Protocol, and what this does is it gives you a mapping between the Ethernet address, that physical or hardware address or Ethernet address at the lowest layer, and the internet layer, which is the logical addresses. And so what it'll do is it'll look at all the devices on your local network. This only works on the local network. If you're on it won't show you remote devices because you're not on the same network, but it will show you everything on your local network and map the internet address that's currently assigned to that device with its physical hardware address. Some other protocols that, well, some of these we've already sort of mentioned, but a few of these are kind of geared directly toward Internet of Things type applications. And so those are one wire, which is a little bit misleading, and it kind of implies that you can do communications with one wire, but remember you still need a ground wire. But it's a digital wire. You just have one wire that gives you both power and data, and you can do communications with low power devices. It's not designed, to power a whole PLC or a robot, but it's good for sensors. It's very useful, and as a matter of fact, most PCs use this one wire protocol to talk to the temperature sensors built into the motherboard of your PC. And then, of course, there's Bluetooth or Bluetooth Low Energy. So the Bluetooth Low Energy is used for sending just small amounts of data from sensors over to another device to receive them. And then, of course, there's Wi-Fi and cell and Ethernet. And then there's the CAN. CAN is a controller area network. This is very popular in like automobiles and airplanes. All right. Now the one wire, you can think of it as a network or a bus. That's kind of why I have it on both slides here. But the one wire is again very handy. But there's a couple of other ones that are available. There's I2C, and this is integrated circuit to integrated circuit is what this stands for. And so what it's a faster protocol. It's fairly fast protocol. I mean, it's not like Ethernet speed or anything like that, but it allows you, it's fairly simple to use, and yet allows you to send quite a bit of data. Again, we're not talking Ethernet or even Bluetooth speeds, but quite a bit of data between two small devices. SPI is another one. It's a slightly more complicated than I2C, but it's very common also. All right, so this one wire protocol here, as I mentioned before, you often find this in like your motherboard. It's something you don't directly access usually, but it actually monitors like the temperature. There's temperature sensors that are using this one wire setup to measure the temperature of your processor, to make sure your processor doesn't overheat or things like that. And there's software that you can install which will allow you to actually view those and have a little display in your system task or something on those. Okay. Now this is a digital bus, and so you can put these different devices on it, and so you can have a 64-bit address. So again, when you think about how many devices can I put in this, well, that would be 2 to the 64th power, okay, which is a huge amount theoretically that you could put all on the same network. And but each device again is going to have its own unique address, and these addresses are built right into the device at the time that it's manufactured. Usually, some of the larger devices you can maybe change them, but most of the little devices you can't change them; they're just fixed. Okay. But a lot of these devices are just like the size of just like a little transistor. And all this one wire network requires is that you have a 4.7 kilo ohm pull-up resistor on the network, because if you're sending power to these devices, but when you send data, that actually has to drop to a 0. So you need to make sure that this data line is pulled up to a high when you're not, when somebody isn't forcing it to a load to be a 0. All right, so we already kind of talked about these networking tools on Windows here. We have IP config. Again, this IP config is Windows only, and there's a /all option you can type, which will give you more information. And then on the BeagleBone, if you're trying to test the BeagleBone, we have there's a extra service that is running on our BeagleBone called Cloud9, and it gives you shell access so you can run some basic shell commands, including testing the network. And so to do that, we have the first thing you have to do for most of these commands is get administrative privileges, which is called the super user. So there's a command called super user do, or sudo, which will allow you to do one command as super user. And a lot of people frown on this, but what I like to do is sudo space super user, and this will give you full administrator access. And this dash here will actually give you it'll pull in the administrator's environment, which will make life a little bit easier. You don't have to put that there, but if you do, you need to make sure you have the spaces here as indicated. And as I mentioned before, the command to test this, to look at your local IP configuration, is IF for interface. And then we have the ping command is available, of course. If you want to look at your routing, you can run the route command. And if you need to change or set your DNS, you can run this command down here, echo name server into resolve.conf. Now to do this, you must run this sudo su command. If you just do sudo, this command will not finish. It'll do the first part fine, but when it gets to this greater than, the greater than piece will not be run as the super user, and so this command will fail at that point. So that's it for this part of the slides.